Okay, one of the conics we'd like to discuss is called the ellipse. And what the ellipse is it's the set of all points xy. So those are the blue points that I have here. I've chosen an arbitrary point, an arbitrary blue point, and labeled it xy. So it's the sum of all points such that the distances d1 and d2. So I have these two distances, and these are the distances from any point on the ellipse to two fixed points called the foci. These are the two foci. Here's one focus, here's a second focus. Together we have two foci. So the distance from any point on the ellipse, the sum of the distances d1 and d2 is always going to be constant. So if I look at any point here, like this point here, this distance here from that point to this focus, plus this distance here from the same point to this focus, that distance, will be a constant always. It'll always give you the same number when you add them up. All right? And that's what the focus is defined as. It's kind of like if you took a string, um, pinned the ends of the string down, and then put a pencil up here and held them taut and just went around. This is the kind of shape that you would make where the pins are going into the table would be the two foci here. Okay, and obviously since it's the same length of a string, the sum of the two distances, the one part of the string and the other part of the string, is going to always be a constant. All right. So there's some terminology we want to look at, and also some relationships, some physical or geometric relationships. The first one is the major axis of the ellipse. Okay, so the major axis of an ellipse is a line that goes through the center of the ellipse. The center is at h comma k. So you see the x value of the center is h, the y value of the center is k, and it also goes through the foci. So from the center it goes out to the foci, and the intersections of this major axis with the ellipse, these points out here where the major axis actually touches the ellipse, are called the vertices of the major axis. All right, so the major axis here, you see this ellipse is wider than it is tall. That's why we call this an ellipse with a horizontal major axis. So the major axis basically it's a line that goes through the center and both foci. There are ellipses also that have major axes that are vertical. Those ellipses are taller than they are wide. But we'll take a look at that in another video. All right, so here's one relationship that we need to know. The distance from the center, the distance from the center of the ellipse to both of these vertices on the major axis. So here's one vertice of the major axis. Here's a second vertice. Remember, those are the points where the major axis intersects the ellipse. So those 2 points are both a units away from the center of the ellipse. I'm going to name this distance a. So that distance from the center to a vertice on the major axis, I'm going to call A. So actually, that gives me a few other relationships. If I can find H and K, if I can find HK, then I know this point over here is just going to be K plus A, comma K. Oops, that's wrong. Not K plus A. We're starting there at H, right, on the x-axis. So horizontally is going to actually be H plus A, comma K. That's because this point here, the center, has an x value of H. I am moving from that point horizontally a units to the right. So the original x value of H has to have a added to it to get the x value of this point here. And likewise, back here, the center's x value of H, since this distance is also A, has to have A subtracted from it to get this point right here. So that ordered pair is actually H minus A comma K. So that's how you find the vertices of um, the major axis. You would take whatever the value of A is, and you would add it and subtract it to the value of H in the center. So if you take the center's X value, H, and you add and subtract A, that's how you find the vertices of the major axis when you have a horizontal major axis. Okay, when the major axis is horizontal, there's another thing we can look at called the minor axis. If the major axis is horizontal, the minor axis would be vertical. So the line through the center of the ellipse that is perpendicular to the major axis is called the minor axis. The intersection of the ellipse and its minor axis are the vertices of the minor axis. So we already have our vertices for our major axis. Now we're seeing here that there are also vertices for what is called the minor axis, which also goes through the center, just like the major axis does, but it's perpendicular to the major axis. So if you have a horizontal major axis, that means your minor axis will be vertical. If you have a vertical major axis, that means your minor axis will be horizontal. Take a look here. Here is the major axis when it's vertical. This is what it would look like. Vertical major axis, because the major axis has to go through both the center and both of the foci of the ellipse. So the major axis here would be vertical. The points up here would be above and below the center, and the minor axis would be horizontal. So right now, in this video, we're only looking at the ones that have horizontal major axis, which makes the minor axis vertical. What we're going to do when we graph these things is we're going to find where the center is. We're going to identify the vertices of the major axis, whether they be horizontally to the left and right or vertically above and below. And we're going to find the vertices of the minor axis, wherever they are. We're going to graph those things along with the center, and then we're going to connect those dots to form the ellipse. Also, we're going to have to graph the foci. It has some added points that we need to identify. Okay, so how are we going to go about this? Well, let's see. Here's another relationship that I want to make here. The minor axis that we just defined, the distance from the center to the vertice of the minor axis is always b. So remember, the distance from the center to the vertice of the major axis was a, and now we find that the distance from the center to the vertice of the minor axis is b. All right, so b. That means that gives us some information here about these ordered pairs here. This one, this vertice, and the vertice of the minor axis down here. Well, since this center point is HK, and it's always HK, just like for a circle, right? Then since that center point is HK, then this point up here is going to be H. The X value is the same because it's above, but it's going to be K plus B. K plus B. And this point down here is going to be H comma K minus B. Okay, so we have those ordered pairs. They're all looking nice. All right, now we've dealt with the major and minor axis. The next thing I want to tell you is that this relationship exists. The distance from the center to either of the foci, the distance from here to here, and also the distance from here to here, because it's the same distance, that distance is c. That distance is c. So that means that I have here this ordered pair having the x value h plus c comma k for that focus, and this focus over here has the ordered pair H minus C, comma, K. So there you have it. That is the ordered pair for each one of the foci of the ellipse. All right, so let's see. There's a relationship actually between A, B, and C. This is the relationship between A, B, and C. Well, if you choose this vertice right here, remember by definition, the distance from the any point on the ellipse to both foci, when you add it up, you have to get some constant. Let's see what that constant is. Well, this distance here between this point and the focus, the vertice of the major axis and the focus, that distance there is this entire distance A, the entire distance from the center to that vertex of the major axis is A minus the distance here, which is C. So this little distance right here, this little gap, the distance from this vertex to this focus is A minus C. So the distance there is A minus C. All right? By the definition of an ellipse, that distance plus this distance from the vertex here to the other focus, when I add those two together, I should get a constant. Well, what is this distance from here to here? Well, this distance from the vertex to the center is always A, we said. The distance from the vertex of the major axis to the center is A. And then the distance from the center to the focus is C. So this entire distance then is A plus C. So I add to that A plus C. This is the distance. This is the distance that is that constant distance whenever I take any point on the ellipse and I add up the distance from that point to each of the foci. This is the constant that I should get. That constant is 2a. And 2a is really just the length of the major axis. The length of the major axis, okay? So it turns out that 2a is that constant distance. Now let's take a look at this triangle here. You see, it's a right triangle because this is one half of the minor axis. This is just a line connecting 2 points that are on the major axis. So there's a right angle right here because the minor axis and major axis are perpendicular. So this right triangle then means that this side over here, this length right here, is the hypotenuse of a right triangle. And since it's the hypotenuse of a right triangle, it's going to equal the square root of b squared plus c squared. This distance from this vertex of the minor axis to this focus right here is b squared plus c squared. The same here. The distance from this vertex to this focus is the square root of b squared plus c squared. Whole thing. All right. So that means that the sum of these two distances has to equal 2a, because this is a point on the ellipse and this is the distance from that point to this focus. This is the distance from that point to the other focus. When I add those two together, the square root of b squared plus c squared plus the square root of b squared plus c squared. When I add those two together, I should get 2a. That's the constant that I have to get anytime I take a point on the ellipse and I add up the distances between that point and each of the foci. That's what I should always get. That's the definition. So we get 2 square roots of b squared plus c squared is equal to 2a. And you can divide both sides by 2 to get that the square root of b squared plus c squared is equal to a. And we get this relationship, that b squared plus c squared is equal to a squared for any ellipse. For any ellipse, b squared plus c squared is equal to a squared. So let's go about trying to find a, b, and c. Excuse me. Let's go about trying to find a, b, and c. All right. So here we have a question or a problem to do. It says find the center, foci, and vertices of the ellipse and then graph it, okay? In order to do that, I'm going to give you the relationship between the equation and all the things that we just discussed. What we need is we need to look at this, which is the form that we want to put that expression or that equation that we have there in. Actually, this should be an equation. This should equal 0. I'm sorry. So that's the equation. All right. So we want to put that in this form right here. X minus h squared over a squared plus y minus k squared over b squared is equal to 1. We want to put it in this form. And when we put it in this form, we'll be able to find hk, which is going to be the center, if you recall. The center from the beginning was defined at hk, the center. So we're going to look at the center being hk. We're going to look at the distance from the center to the vertices that are on the major axis is a. Remember we said that? The distance from the center to the vertices that are on the major axis we said was a, from the center to the vertices that are on the major axis. So if we can find a, we can find that distance there, and we can find the ordered pair. All right, and the distance from the center to the vertices on the minor axis is b. So if we can get this equation here into this form right here, I'll have everything I need. I'll have h and k to find the center. I'll have a, so I can go from the center to the vertices of the major axis. I'll have b, so I can go from the center to the vertices of the minor axis. And with this thing that I just found here, with this relationship, if I know a and b, I can always find c with this relationship. So I'll be able to tell also where the two foci are, where the foci lie. All right, so let's go ahead and try to get it in this form. Let's go ahead and try to get that equation in this form. Let's bring it down a bit and bring this up. So that's what I'm aiming for right there. And this is what I have so far. So what I need is I need to have two binomials being squared, and I need to have denominators that are constants. All right, so what I'm going to do here is I'm just going to go ahead and I'm going to complete the square on x so I can get an expression like this, a binomial squared. I'm going to turn 4x squared and 32x into a binomial squared. And I'm going to do the same thing for y. I'm going to take the two y's and group them together. So I'm going to complete the square on both x and y. That's the process that I'm going to go through. So first I'm going to group the terms together to make it a little easier to see. 4x squared plus 32x plus 9y squared, 9y squared minus 90y, 90y. And I'm going to put this constant on the other side by subtracting it from both sides, minus 253. All right, so now what I'm going to do is I'm going to take the quadratic and linear x terms and I'm going to factor out the leading coefficient so I can have a leading coefficient inside of my parentheses of 1 so that I can complete the square. So I'll have 4. I'm factoring out the 4 out of only these two terms, x terms. So I'll have 4x squared plus, and 4 goes into 8, 32 8 times 8x, and then plus, and then I'm going to factor out of these two terms, out of the y's, I'm going to factor out a 9 so that this leading coefficient for y can be a 1 also. So that's going to be y squared minus 10y, and this is still equal to negative 253. Okay, so now what I want to do is I want to go ahead and I want to figure out what number I have to add to these two terms to make it into a perfect square trinomial. I think it's going to be half of this term, half of the linear term's coefficient, squared. Well, half of 8 is 4, and 4 squared is 16. This is what we're doing. We're doing half of 8, and we're squaring it. Half of 8 is 4. 4 squared is 16. So that's the number we're going to add into both sides for, well, not actually, because I'm adding it inside of a parenthesis here, 8x. So when I add this 16 in, this magic number, I'm not actually adding in just that 16. I'm actually adding in 16 times the 4 that's in front of the parenthesis that the 16 is inside. Because that 16 is inside a parenthesis, what you're actually adding globally is the 16 times whatever is in the front of that parenthesis. So you're only adding the 16 locally, but globally you're adding 16 times 4, 64. So I'm adding 64 to the left side. So in turn, I also want to add 64 to the right side, plus 64. So once again, I'm adding in 64 because uh, I'm actually adding in the 16 inside of the parenthesis multiplied by the 4 on the outside. All right, now let's deal with y. Still working here. I still have the plus 9 here. And let's see, what do I have to add in here in order to make this into a perfect square trinomial? Well, that's going to be half of this term. Well, half of this term is negative 5, and then negative 5 squared. Negative 5 squared, so it's going to be 1 half times 10, whole thing squared. Once again, that gives me 25. So that's the number I'm adding inside of the parenthesis here. So on inside of the parenthesis, I have y squared minus 10y. And on the inside of the parenthesis, I am adding 25. But globally, I'm actually adding a 25 times 9. I'm actually adding 25 times 9. So what I'm really adding, 25 times 9 is 225. So plus 225. So add those things into both sides. I add in here a 25, which actually turns out to be 25 times 9. And I add here a 16, which actually turns out to be 16 times 4. Okay, so now what I want to do is I want to go ahead here and I want to factor both of these trinomials that I've created, these perfect square trinomials. This first one, I'm going to factor it as x plus 4 squared plus 9 times. The second one, I'm going to factor it as y minus 5 squared. And it's equal to, well, this sum here is going to give me 36. Okay, so I get this. And remember, my goal was to make it be two binomials squared, and on the other side of the equal sign should be a 1. So to get a 1 over here, what I'm going to do is I'm going to divide everything by 36. So my next step here is I'm going to divide this by 36, this by 36, the entire thing here, and this by 36. So there's 3 terms. I divide each term by 36. That allows me here to cancel 4 over 36. So I get x plus 4, which I can write as x minus negative 4, just so it fits the formula. And then on the bottom, I have, well, it was 4 over 36, which is 1/9. And then plus, and then it's y minus 5 squared, y minus 5 squared over, well, 9 over 36 is 4, and this is equal to 1. So let me rewrite it just one more time. I'm going to have this as x minus -4 squared over, I'm going to write this as 3 squared, plus y minus 5 squared. I'm going to write this as 2 squared. And then this is equal to 1. So now it fits exactly the form. X minus h squared, oops, x minus h squared over a, x minus h squared over a squared, plus y minus k squared over b squared is equal to 1. So that was the form. I think I might have written it wrong originally up here. Yep, no, it's right. Okay, so that's the form that we wanted it to be in. So now we can identify h, k, a squared, or a and b. Now we can identify those things. So let's identify them. Let's identify h, k, a, and b. And then we can calculate c. So h is, in this case, -4. H is -4. K is 5. A is 3. Remember, A is the distance from the center to the vertices of the major axis. B is 2. And the only other thing we need to find is C, so we know where the foci are. Well, from this says that B squared plus C squared is equal to A squared. And I know A and B, so what I'm being told is B squared, which is 2 squared, b squared plus c squared is equal to a squared, is what we found out. Or we get c squared is equal to 9 minus 4. And that says that c is the square root of 5. 9 minus 4 is 5, right? And then you take the square root of both sides. You get c is the square root of 5, which is approximately 2.24. 2.24 approximately. So now we have everything we need. We know that C is approximately 2.24. So now we can give every piece of information that we were asked for because we have all those numbers. These numbers are all we really need. Because I know all the geometric relationships. So let's see here. Let's take these numbers down here and answer the questions that we were asked. Well, the first thing we were asked was to find the center. Center is easy. Center is HK. So we can find the center relatively easy. The center is going to be -4, 5. So the center is the point -4, 5. Then it says to find the foci. Well, the distance from the center to the foci, is c. So that means from -4, 5, I have to go a distance of about 2.24 to get to either of the foci. And since the major axis is horizontal, and I know that because the larger number a is underneath x in the formula, You see that? The larger number here, the larger number is underneath x. 3 squared is 9, 2 squared is 4, 9 is larger than 4. It's associated with x. That's how I know the major axis is horizontal. So I'm going to go horizontally, c units from the center. So if I go horizontally c units to the left of center, well, from negative 4, if I go 2.24 to the left, I'm going to be at negative 6.24. And of course, since I'm going horizontally, the y value will not change. So that is one of the foci. And then the other one is going to be the same distance but to the opposite side. So from here, from negative 4 comma 5, I'm going to go 2.24 units to the right. So 2.24 units to the right is going to take me to negative 1.76 comma 5. So those are the coordinates for the foci. Then the vertices. That's the next thing we're asked to find, the vertices. So we have two kinds of vertices. We have the vertices that are on the major axis. Well, the vertices on the major axis are both a units away from the center. And since the major axis is horizontal, they're a units horizontally. So a units to the left of the center is going to be, well, a is 3, so that's going to be negative 4 minus 3, negative 7. And then a units to the right of negative 4 is going to be uh, negative 1. So the foci and the vertices of the major axis are all on the same horizontal line. They all have a y value of 5. And then there are the vertices of the minor axis. Well, for the vertices of the minor axis, those are both b units away from the center, but they're b units vertically, up and down. So b units from negative 4, 5 up is negative 4 comma 7, because we're adding 2 to the y value. And 2 units down would be negative 4 comma 3. So those are the vertices. And then all we have to do to graph this ellipse now is graph all those points. Well, the center the center is not actually on the ellipse. It's negative 4, 5. Negative 4, positive 5. That's the central point. That's the center. Negative 4, 5. And then from there, the foci are negative 6.245 and negative 1.6. So negative 6.24, 2, sorry, 2, 6.245 and negative 1.76, which is somewhere in here, 5. So we get those 2 points would be our foci. And now let's graph points that are actually on the ellipse itself. So these vertices are actually points on the ellipse. So the vertices are negative 7, 5 and negative 1, 5. So we have negative 7, 5, negative 1, 5. Those are the vertices of the major axis. And then the minor axis's vertices are negative 4, 7 and negative 4, 3. Negative 4, this is 5, 6, 7, and negative 4, 3. So the ellipse, it looks something like this. All right, the ellipse looks something like that. We've identified the center, the foci, the vertices of the major and minor axis. All right,